Hey, if you're a chemical engineering student, you already know that fluids are, well, at the heart of pretty much everything we do. From massive industrial reactors to the simplest pipes, you've got to understand how fluids behave. It's totally non-negotiable. So in this explainer, we're going to break down the absolute fundamentals, the core properties that govern every single fluid you'll ever work with.
So here's our game plan. We're going to start with the absolute basics. What even is a fluid? Then we'll build out what I like to call its stat sheet of key properties. After that, we'll get into the difference between a perfect textbook ideal fluid and the real thing. Then we'll dive into the really cool stuff, the world of Newtonian and non-Newtonian fluids, and finally, we'll see exactly how all this plays out in the real world of engineering.
Okay, let's dive right in. At its very core, what's the actual difference between a fluid and a solid? It's not just about being runny. The real answer, the engineering answer, is all about how they handle stress.
To get your brain warmed up, just think about this for a second. Stirring a glass of water takes almost zero effort, right? Your spoon just glides through it. But a thick bucket of paint, that stuff fights back. It feels heavy, almost sticky. They're both fluids, so what's the deal? Keep that question in the back of your mind, because we are absolutely about to find the answer. And here it is. This is the crucial point. When you apply what we call shear stress, just imagine trying to slide the top layer of something like a deck of cards. A solid might bend a tiny bit, but it fights to hold its shape. A fluid, on the other hand, just goes. It deforms continuously. It flows. For as long as you apply that force, the fluid just keeps on moving. That continuous deformation is its defining feature.
So that leads us right to the official textbook definition. A fluid is anything that can flow and take the shape of its container, and that includes both liquids and gases. Now, for us as engineers, the really critical distinction is compressibility. For the most part, we treat liquids as incompressible, meaning their volume stays constant. But gases? Oh yeah, they are highly compressible and their density can change like crazy with pressure.
All right, now that we know what a fluid is, how do we describe it with numbers? Every fluid has a set of core properties, kind of like a character in a video game has a stat sheet. These are the numbers that tell you exactly how that fluid is going to behave in your system.
First up is mass density, which we show with the Greek letter rho. This one's pretty intuitive, right? It's just how much stuff, or mass, is packed into a certain space. A liter of mercury is way, way heavier than a liter of water, and that's just because its density is so much higher. Simple as that.
Next up, and this is arguably one of the most important properties you'll ever deal with, is dynamic viscosity, or mu. This is a big one. It's a measure of a fluid's internal friction, its resistance to flowing. The easiest way to think about it is just as the thickness or stickiness of the fluid. Honey has a super high viscosity, water has a really low one. And always remember, this property is incredibly sensitive to temperature. Just think about how runny honey gets when you warm it up.
This little table here basically brings our key stats all together. We just talked about mass density and dynamic viscosity. You're also going to constantly run into kinematic viscosity, which is really just the ratio of viscosity to density, and surface tension. For any of you diploma students watching, this is a perfect summary for your notes. Seriously, you might want to grab a screenshot.
Okay, so every engineering student learns about the ideal fluid. It's this perfect theoretical concept that makes the math way, way easier. But it is so important to understand how it's different from the actual stuff you'll be pumping through pipes out in the real world.
And this slide really shows the divide, doesn't it? An ideal fluid is a complete fantasy. It has zero viscosity, no stickiness at all, no surface tension, and it's perfectly incompressible. A real fluid is what actually exists. It has viscosity, it has surface tension, and it can be compressed. Let me be clear. As an engineer, you will always be working with real fluids.
Okay, now we get to the part where fluid behavior gets really, really cool. By putting these real fluids through a kind of stress test, we can see how they respond, and that separates them into two major families.
On one side, we have our Newtonian fluids. For these guys, like water, air, gasoline, their viscosity is a constant property, as long as the temperature stays the same. It doesn't matter how fast or slow you stir it, its thickness doesn't change. But on the other side, you've got the non-Newtonians. These are the weird and wonderful fluids where the viscosity itself actually changes depending on how much stress you apply. Remember that paint from the beginning? It definitely belongs in this category.
So let's dive a little deeper into these non-Newtonians, because this is where the fun stuff happens. First, you have pseudoplastics, which are also called shear thinning. These get less viscous the more you stir them. Ketchup is the absolute classic example. It's stuck in the bottle, but after a good shake, it flows easily. Then you've got the total opposite, dilatants or shear thickening fluids. Their viscosity increases with stress, like that famous cornstarch in water mix. And finally, you have Bingham plastics, like toothpaste, which won't flow at all until you apply enough force to get past a certain yield stress.
So why did we just spend all this time on theory? Because understanding these properties is literally the difference between designing a system that works and one that fails, sometimes catastrophically. This is where all that knowledge becomes power. I mean, just look at these applications. A fluid's viscosity tells you exactly how powerful a pump you're going to need. If you're designing a food processing line, you have to know the ketchup is shear thinning so you can make it flow correctly. The drilling mud used for oil rigs, it's engineered as a Bingham plastic so it can carry rock cuttings up to the surface, but then turns solid when the flow stops. It's all connected.
You know, this really is the bottom line. As the source material puts it, understanding these phenomena is critical for engineering applications. Every single calculation you make, every piece of equipment you choose, it's all going to come back to these fundamental properties we just talked about.
All right, let's end with a quick concept check just to lock all this in. Based on everything we've just covered, think about this classic experiment, a mixture of cornstarch and water. It feels totally liquid when you stir it slowly, but it becomes hard as a rock if you punch it. So, which type of fluid is it? I'll give you a second to think about it.
If you said dilatant or shear thickening, you nailed it. You got it exactly right. The slow stir is a low shear rate, so the viscosity stays low. But that punch is a super high shear rate, which causes the viscosity to spike dramatically, making it feel solid. This is just a perfect hands-on example of why these classifications matter so much. And understanding this stuff is your first big step to really mastering fluid mechanics.